All right, welcome back. We're only going to have one lecture this week because of Thanksgiving. I'm pretending that this is a Tuesday-Thursday class, right? So we just have one this week. So we'll get some programming and some non-programming in today. So where we ended last time was we were talking about this beautiful thing called recursion, where you were finding problems inside of themselves. So we talked about factorial, like, oh, we found 4 factorial, inside of 5 factorial. And we noticed that there's a rule that we can follow, that n factorial, if we generalize it, n factorial is always equal to just n times n minus 1 factorial. And so the problem got smaller, and that is what it means to be a recursive algorithm. And so the very last thing we did was come up with the actual code for this, and we're going to go and implement that now. So in code in Python, in any programming language, when you have a recursive problem to solve, you'll usually write a function about it to go and solve that problem. And a recursive function, because it's defined in terms of itself, the problem is because of that, you have to solve the problem inside of itself. And if it is the function that solves the problem, then a recursive function must therefore call itself, which is interesting. So you'll have to discern whether or not you are in the base case or the recursive case in each time you get called with some n. Okay, so it's always fact of n, like we're going to call fact of 5 eventually. And, well, you have to figure out, okay, am I in the base case or am I in the recursive case? Okay, and we translated that in math into code. Yeah? Okay, we are essentially ready. And so the idea is that fact 5, when we first give it fact, it's going to start executing this program. It's going to notice, oh yeah, n is 5, it's not 1. So it's got its n that it's worrying about. Well, it's not 1, so I'm not going to return 1. I'm going to store in x the value of fact of n minus 1. And so then I'm going to go off and call fact of 4. So this is like fact of 5 stuff. Fact of 5 is going to call fact of 4, who's going to have his own little n. N is 4 for him, and then has its own x that it's going to build up. So it'll also hit the recursive case. And so fact of 4 will call fact of 3, and so on and so forth, until we hit this base case. So let's code this up, and then I'm going to give you an example as to why this is making any sense at all. All right, so let's go to code. We already technically coded it on paper. Let's just do it for real now. And let me make a new file. This is going to be a fun one that we'll get to later. Maybe I'll just minimize that. So, yeah, we can just put it like this. So let's maybe I'll just make one big file about a few different examples. So I'll call this recursion.py. And, all right, a factorial. This is what it does. We got called. We got called with some n. Somebody's asking us fact of something. We needed to figure out, okay, was it the base case, in which case I'm done, I know the answer, or was it the recursive case, in which case I needed to do more work. All right, so figure out if we're in the base case or the recursive case. In the base case, we can immediately return if n is 1, we immediately know the answer without doing any extra work at all. We're just going to go and return 1. That's the answer in that case. Otherwise, we're in the recursive case. We need to build up our answer using the smaller subproblem's answer. So we're going to save that answer in x. Fact of n minus 1. It's going to go off, call ourselves on a smaller answer, so it's always going to eventually get to this case and build itself back up. Calls fact of n, and then we return n times x, because x was fact of n minus 1. Yeah? Technically, I don't need this x, but for demonstrative purposes, it's better than just putting it right here. I'm going to show you how it builds up the solution. Okay, so that's fact of n, and so I can go and use it now. I can say print fact of 5. What answer might that be? Well, we know what it should be already. 5 times 4 times 3 times 2 times 1, whatever that is, 120, and we can confirm that in code by just writing it out in the REPL. Ah, yes, that's correct. So why did this give us the right answer? Why did this work at all? And so I'm going to have a couple slides about why it does this and how it works. So let's go back to Python. And I'm going to draw things in a weird way. It's called a stack diagram. Tells me which function's called which. So the first function that got called, it's like a stack of dishes. So the first function that got called was fact of 5. So it was fact, and how did we know it got called with 5? Well, that's its n. Its parameter n got called with 5, and it hit the recursive case, so it's trying to put something in x. It's like, I don't know what it is, I'm going to call fact of 4 to put it there. Okay, so we are sitting in fact of 5 right here, because it's waiting to fill in x with fact of 4. I hope that makes sense, because our n is 5. We want to fill in x with fact of 4, and in that case, after we get back that answer, we can finish off this function. But we're not done yet. We have to wait. This fact has to wait for fact 4 to finish. So here's fact of 4. Its n was 4. And again, it's not the base case, so it needs to go off and calculate its x. It's like, all right, well, I'm not in the base case, so I need to calculate fact of 3 now, because my n is 4. Oops. I need to calculate fact of 3, please. Go off and do that. Tell another version of myself to do that. And then in that case, once I get it back, I can finish what I was trying to do. So fact of 4 calls fact of 3, and I think you can understand what's about to happen. It's just everybody's going to hit the recursive case for a while. Fact of 3 calls fact of 2, and it's 2, x, we don't know yet. And then finally, fact of 2 calls fact of 1. The n in that case is finally 1, and we hit a different spot in the code. Fact of 1 hits the base case and gives back, returns 1. So the answer that fact of 1 gave back to fact of 2, who was waiting for it, was waiting right here, so it could fill in its x with fact of 1, because its n was 2. It got back 1, and this guy kind of vanishes. It's like, okay, I'm done with my work, back to fact 2. Okay? So normally he's going to, like, you can imagine me erasing this, but I'm going to keep it here so that you can see it for when you review this. Okay, so now the x is no longer a question mark. That's an ugly question mark. The x we can now fill in because the x was 1. What I got back was 1. The answer for x is 1. And my return value is my x times my n, because that's what I was supposed to do. Calculated my fact of 1, I got the answer, put in my x, and now I'm going to return back, give back to whoever called me, n times x, which was 2 times 1 in this case, because I got back the 1 from fact of 1. Okay, it's all going to start building itself up now. So this guy, fact of 2, returns 2, and that's the answer for 2 factorial, remember. All right, so then this one got back the 2. It knows to put it in its x. It was waiting for it. Going to put the 2 there. Bam. There goes the 2, and now it can do its work. It's like, ah, yes, I was waiting for you. I was waiting for fact of 2. Now I'm just going to return my n times my x. That's 6. Yeah, it's all working. It's all coming together. So then, fact of 4 was waiting for fact of 3 to finish. It just finished. And all these guys, like, get rid of themselves, of course. Now we're back in fact of 4. I'll just get rid of these question marks because they're about to be finished. Okay, back in fact of 4, it was waiting for fact of 3. It finished, it got its 6 back, and now it knows to return back its 4 times its 6. So, it gives back 24, right? I think so. 6, 12, 18, 24. Yeah. And so then fact of 5, who was waiting for fact of 4 to finish, well, it got back the answer, finally can put it in its x. And now, fact of 5 is done. the first function that I called is now done. Technically, there's a call to print underneath this guy, and so fact_5 returned back 120, which was its n times its x, to print. Okay, I hope you see how that's working, and hopefully it makes sense. So that is recursion in a nutshell. Excuse me. And what it's doing is it's eventually just making smaller and smaller problems that are easier and easier to solve, and eventually it gets to the base case and can build itself on back up down the line, down the stack, as we say. Okay, so that's factorial. Super cool. All right, I have more examples, but first let's talk about why in the world this even works at all. So maybe my example was too hand-wavy for you. There is a mathematical reason why this works. If you're a math major, you'll eventually learn about this. It goes back to an idea called the principle of mathematical induction. Feel free to look that up, but let me prove it to you a bit less hand-wavy now. So the base case, we always had two things for a recursive solution. We had a base case. When do we stop? And that's like, all right, I had a problem P. Maybe P was find the factorial. The base case is like P of 0. It's like the smallest thing. Maybe there are multiple base cases, but there's a small one. Okay, that's what you do. You immediately know the answer when you're at P of 0. Okay, so that's like the base case is giving P of 0. Whereas the recursive case assumed that P of like n had the solution. It assumed that it could get this, and then it found a way to make P of n plus 1, okay, using P of n. Okay, so like if I had this, that's what it's saying. If I have this, I can make this. So that's what the recursive case is doing. Okay? It's saying, given a P of n, I can get you back in P of n plus 1. That's exactly what we did. We assumed the existence of factorial of n minus 1, and we used it to build up the final answer, the bigger one. All right? This might be very vague, but this is very powerful, quite magical. So in order to solve P of 5, for example, we have a sequence of things that we can do now. We start with P of 0 because we always have that. Saying, I know how to solve the smallest problem. So that's using the base case rule. And then, from P of 0, we can get, using the recursive case rule, P of 1. Do you see that? This is the reason why recursion works, and you get to assume that the recursive call works. You use the recursive case rule with n equal to 0 to get P of 1, okay? Because P of 0 will give us P of 1, and we had P of 0. We got it with the base case. We immediately have it. All right? And then we can keep on using the recursive case rule. Because now we have P of 1 to work with. We can use P of 1 to make P of 2. Isn't that beautiful? And we can use P of 2 to make P of 3. We can use P of 3 to make P of 4. We can use P of 4 to make P of 5. And so on until the end of time. We can solve every problem. Okay, so that is a mathematical reason for why recursion works. And you get to assume, in the recursive case, that it works, that the problem gets solved correctly. as long as you build up the final answer with it. Because eventually it will get solved correctly, because you'll start with the base case and then just build yourself up for the recursive case's solutions. So we're kind of working backwards when we called the function, and this is like from the bottom up. But this is why it's working. It's getting down to p of 0, using p of 0 to solve p of 1, to solve p of 2, to solve p of 3, to solve p of 4. It's a very powerful solution, and no pun intended, our next example is the power function. Okay, so let's do this. So the power, function, we'll call it pal maybe, and it'll take I don't know, a floating point number like a float and then an int. It'll do that. Okay. So that's we want that to return 2.5 squared, or maybe let's give another one to the power of 5, because it's always an example. It's always a good thing to build out your example. So we want this to work. We want to find the recursion in the calculate a power operation. If only I could draw. There we go. All right. So the idea is, okay, notice 2.5 to the 5. We need to find a smaller power computation inside of this. That's what it means. I'm claiming that this is a recursive problem. Equals, okay, let's expand it. Let's see if this works. 2.5 times 2.5 times 2.5 times 2.5 times 2.5. 5 times. Do you see a smaller problem? A smaller power computation problem? Let me know. Hopefully, you also see, well, either side works. Here is 2.5 to the 4. You see that? So, generalize this to a recursive case. N to the m equals n times n to the m minus 1. Very similar to factorial. So it's like 2.5 to the 5 is 2.5 times 2.5 to the 4th. It gets smaller and smaller. And eventually, you need to stop. Okay? When's your base case? You're not going to keep on multiplying 2.5 times 2.5 times 2.5 to the negative 2. You're going to stop somewhere, right? You're going to stop before you get to the negative powers. And I think you'll stop on the 0th power. That's the most general thing. N to the 0 is always 1. Okay, so that's your base case. That's your recursive case. And I hope it makes sense as to why this is all working. In code now, we get to make a recursive call with a smaller power. This is recursive because the exponent gets smaller each time. Okay, that's the idea. So that is power. And let's go and code this now. So we're going to translate this math, into code. And I guess I'll use n's and m's. Why not? So def pow n to the m. So this is supposed to compute n to the m recursively. So we can just read off our answer now because we did the work. So figure out for then the base case of the recursive case. So if m is equal to 0, because m is our exponent, remember? M is our exponent. If it's equal to 0, return 1, because anything to the 0 power is 1. Otherwise, return, and now I'm not going to build up the intermediate answer. I'm just going to return one big thing, including the recursive call, and I'll just finish it before it returns. Return n times pow n m minus 1. Okay, I hope you see this. Just using the rules of powers, these are equivalent, and because this is getting smaller, it's a correct recursive algorithm. It's very fancy. And so if you get to expand this, I encourage you to draw this table, because gosh, is that a great diagram, and it helps you understand it. But let me show you that, I don't know, what's one that we know? Maybe like 2 to the power of something? Or no, we can just do 2.5 to the 5, why not? Pow. 2.5 to the 5. What is that? Let's find out. Well, appears to be 97.7-ish. And we can confirm that by doing Python's normal to the power of operator. And oh man, do we get the same thing? Yeah. So this is another way to calculate the powers, and we kind of like rolled our own this time. Power computations, beautiful. Okay, one last example. It's using a concept called divide and conquer, and this is an extra powerful concept. It's a very silly example that I'm going to give, though, but trust me, if you go any farther in your computer science career, you will encounter divide and conquer, and it will be very, very helpful for you. Okay, so let's just define it. A divide and conquer algorithm. So it's technically an adjective. An algorithm is a divide and conquer kind of algorithm if it breaks its problem into subproblems. Now that's just the definition of recursion, breaking a problem into subproblems. There's something extra. And the fact is that they are equal sized. Okay? And I should be a bit more specific even. It's going to break its problem down like by a factor each time, okay? Usually the factor is 2. So for example, a recursive algorithm that works on a list would split this list in half and work on this half and then this half separately. And then recursively, of course, it would take this list, split it in half, and work on that, and just build up the answer, smaller lists at a time. So what I'd like to do is give you a very silly example, but it'll illustrate the problem. It's not any more useful to do it this way, but it's a good example, I think. Let's see here. Let's pretend we want to add all the elements of a list together. So if I have 8 ones, that's going to eventually give me 8. Like I want a sum function. Sum of L should give me back 8. Yeah? And one way that we can do it is just iterate through every possible index, like L of I plus 1, L of 0, L of 1, L of 2, L of 3. Or we can make recursive calls and be like, all right, sum the smaller half of this list, sum the larger half of this list. So eventually, we'll get to this kind of problem. We're like, okay, first we sum the left half, the smaller list. And then this one's do the same for the right. Okay, and then they go off recursively, splitting their lists in half. It's like, all right, what's the sum of 1, 1? What's the sum of 1, 1? And the answer is always going to be, well, whatever you get back, just add them together at the very end. This will make more sense when I code it up. And these are the same as those. And these are just sums of tiny, tiny lists, just with ones in them. And that can be a base case. Or maybe the empty list can even be a base case. So this is the idea, and just a bunch of tiny ones, lists of just ones in them, sum those together to get 2, 2, 4. 4 on this side makes 8. You see how I'm doing that? I'm splitting the problem each time in half. And it's a silly example, I know, and this is not something I'm really going to test you on, but it's just good to have seen once. So let me just code this up very, very quickly. The name of the function, we'll just have it be sum, and it's going to take a list L, a low index, and then a high index. So sum will sum the indices of L from low and high inclusive. That's the idea, and get back that answer. So I'm just going to go a bit faster this time, but don't worry, I'm not going to like test you on all this, make you come up with your own. So this is just a good example. I'll say, okay, L, we need to figure out the base case. And I think there might have to be two base cases. Base case 1 is the list is empty. So the way that a list might be empty is we're going to call this function like this, like print sum 1, 2, 3, 4, 5, 6, 7, 8 between indices 0 and 7. So sum all of those indices, the entire list. And the base case can be, all right, when we have an empty list to sum together. And we'll always get the same list. We'll just keep on passing along L, but these low and highs will change. So how do we know when the list is empty? Like 2, 2 is still just the list with index 2 in it. Well, the list will be empty if low is ever greater than high. It's a bit of a weird thing, but I encourage you to draw the diagram for how this is going to execute. Maybe print out how low and high change. But it is quite possible for low to be greater than high eventually. And that means we're done. If low is greater than high, that means the list that we're trying to sum is empty, the sublist, that is. And we just need to return all the things, the sum of all the things in an empty list. There's nothing there, so it's 0. Okay. Elif, there's another base case, and that is if low is equal to high. So in that case, we can say return L of low, or L of high, they're the same. So base case 2, the sublist has one element. And in that case, like, I know there's only one thing to sum together, sum all the elements in a size 1 list. Well, I'll just give back that one thing, because that's the sum of them all. Yeah? Base case 2, and then finally the recursive case. Not the else case. Split the list in half, and recursively sum them. So I'm going to calculate the sum of the smaller half. So the smaller side of this list is sum L from low to the midpoint. So we got to calculate the midpoint between low and high. Low plus high over 2. And then we'll calculate the smaller side of the sum. It's low from low to, say, mid minus 1, those indices. And then the bigger sum is, let's call it lower sum and upper sum. Upper sum is from mid itself. We don't want to skip an index too high. Okay. And this right here, this minus 1, is exactly how you can get negative, or a difference that is like this, where low gets bigger than high. Because maybe low and high were the same, which means mid is the same. Mid minus 1 is now smaller than low. Okay? So that is the recursive case, and so it's just going to split them all up, like sum the smaller list, recursively, and eventually it'll hit the base case, either an empty list or a size 1 list, and it'll all work its way back up. So in theory, this will work. Let's find out. Hey, what have I done wrong here? L of low. Oh, shoot. When we divide by 0 to get these mids, we sometimes run into issues with, we get like 0.5. There is no 2.5 index in this list. We have to make it integers so that everything works out. And then it should work. This minus minus, or this double slash, what it does is, like here, I have 5 over 2, that's 2.5. We don't like that. That's not a valid index. 5 slash slash 2 is integer division. Drops the decimal places, which is exactly what we want here. That's a valid index now. And then finally, we actually have to do the summing. Right now, it's an infinite loop. That's called a stack overflow. Recursion depth exceeded. The answer for the recursive case is the lower sum. That was the sum of the smaller half, the lower half, plus the upper sum. And that'll give me the sum of the entire list. From indices low through high. And so with that, I believe, now we still get an error, and I will have to do some debugging to figure out why. Aha, silly me. So there was a very weird little bug, and I used to have it as low to mid minus 1, and then mid to high. And the way that we did this integer division, I think, messes with that. If I do it that other way, which seems equivalent, it won't work. But if I do it this way, it will. So a bit of magic there. But it does do the right thing, and that was all I was trying to explain anyway. So I think I'm happy with that example. And now let's move on to beauty. Okay, so let's get a bit philosophical and talk about, well, what is beauty? All right. So not that recursion wasn't beautiful. I'll actually talk about some beautiful recursive things in just a second. So first of all, there are a couple camps of what it means to be beautiful. So, and I fall into the subjective camp. So everything that I'm going to talk about is my opinion, but hopefully it's also beautiful to you too. Okay? So the philosophical definition of beauty is, well, there's two possible ones. Something can be defined to be beautiful because it's like ideal. It's the greatest possible example of something. It's symmetric, it's ordered, it's balanced, it has proportion. It's like, this is the world's greatest car because of the way it looks. Like it, obviously it's going to be great. It's all symmetric. It's got fancy rounded corners. Like there's the idea for an objectivist is that there is one definition of beauty, and you can write it down, and somebody can be like, oh yes, that's exactly why this looks beautiful. I agree. And a lot of the time, that's not quite possible, but sometimes it is. Like, yes, this is, I don't know, this is an ideal donut because it's perfectly round, you know? Like that is kind of what makes things beautiful sometimes, I would say. So that's the objective view of beauty. And then the subjective view is when you say that something is beautiful because it brings you some kind of pleasure. Like it's pleasing to the eye, and maybe that's why, like, you can also define, like, yes, because it's balanced. Subjectively, it's pleasurable. So that is why it's beautiful. It's beautiful because I like it. It brings me pleasure. Maybe somebody really likes uneven donuts for some reason, and that is their prerogative. They get to believe that that is beautiful, even though the objectivists might say it's not. All right, so that is the subjective view of beauty, and Kant, in fact, was all about this definition. He thought that this was the right way to define beauty. So I'm going to show you some beautiful examples of recursion, and I'm very excited for that. So the first thing is fractals. I'm sure you've heard of these. Take a look at leaves, for example. A fractal, it's just like you graph a function. Think about it mathematically. It's a function that's what's known as self-similar. So it can be 2D, 3D, as long as it looks similar to itself. So self-similarity means you look like yourself when you zoom in. So just to get an idea of that concept, like think of a pebble. It is self-similar. It's kind of like it kind of looks like a boulder. And a boulder is kind of self-similar to a mountain, but does that mean a pebble is similar to a mountain? Who knows? So that's why it's kind of philosophical. So that is self-similarity in a nutshell, and a fractal is all about that. So you might have seen this famous one. It's called the Mandelbrot set. It's a very famous fractal, and if you just keep zooming in, you end up looking like yourself. Like you can see that this thing is there inside of it, and like different orientations, different sizes, different zoom levels, but it in fact never repeats, which is something very, very interesting about this particular fractal. As you can move in as far as you want, but it's never going to be exactly the same as the outside, which is very cool to think about. So that's the Mandelbrot set in a nutshell. And I want to do something special. I want to cut it up. So you can actually use our friend the turtle to draw the Mandelbrot set, in fact. And if I go to this Wikipedia page where I stole this GIF, or one of these I stole it from, that's the one. We have the definition for the Mandelbrot set. It is just, well, if I zoom in a little bit, it is the set of complex numbers C for which the function f base C of z equals z squared plus c does not diverge when started with z equals 0. So the idea is we have this little function f of c, and we just keep on calling it on itself, starting with f of c of 0. Just keep on doing that a bunch of times, and we want to see if it's bounded, like it doesn't get large, like it doesn't go off to infinity. That's what it means to be in the Mandelbrot set. You're either in or you're out. And so, is there anything else here? Is there a better definition anywhere? There is actual code, and I'll use 100 instead of 1,000, but why not? So yeah, this is the idea. We start with a number z, and then we just we square and then add the value that we're trying to check whether or not it's in the Mandelbrot set. Okay. Is that all I wanted to say here? Yeah, this is the real definition right here. It's like you're calculating a sequence. The first sequence is 0, and then you go based off of the old value, square it, and then add c, because you're trying to check if c is part of the Mandelbrot set. And I'll talk about what all this means in code. So I have pre-coded this for you, but first we need to learn about this thing called nested loops. Okay, and that will lead us to this program. It'll finally make it make sense. So you can put loops inside of loops, in case you were wondering and you wanted to. But what does it do when you do that? So it's quite possible to do this. You can be like, all right, for I in range like 50. And then you'd be like, inside of that, I'm gonna have another loop, please. For j in range 50. Or let's do a different one. Let's be like 25. Why not? I think like do stuff with I and j. What? Because they're both alive at that point up in here. Why would you ever want to do this? So let me actually code this up, and maybe we'll print out I and j. And I'll talk about the case that we need to worry about, the reason this is cool. So for, I'll call this nested loops. Nested loops.py for I in range. So I is going to go between 0 and 49. For I in range 50. For j in range 25. Let's print I comma j. Right? So that just allowed a space in between the two. And if I run this, you can see it going. It's going. It's the first thing's I, the second thing's j. And we go all the way from 0, 0 to 49, 24. And everywhere in between, and that is the key. Okay, a nested loop. It's like you can see it start. Okay, now I is 39. I'm going to go and do this entire loop inside of that when I is 39. I'll set j to be 0, while I is still 39, j to be 1, j to be 2, and eventually it'll get to the end, 39, 24, and start over with a new I. Okay, so it finishes executing the inner loop before it does another iteration of the outer loop. And that should make sense. It's just code. It does all the code inside of the body of the loop, and the body happened to be another loop. One nice thing, the very special thing about nested loops that I want to get across to you right now is that nested loops try all the possibilities. Between some values. So for every number in between 0, 0, I being the first thing, j being the second thing, every number between 0, 0 and 49, 24 is going to be alive at some point in here, okay? Like you can pick, I don't know, 27, 15. That is eventually going to get computed. I will be 27, j will eventually be 15, okay? Every possibility in between these numbers will come up, okay? And so that's all we need to do now in order to code our Mandelbrot set. So what you do is let me turn this off for a second. It's a weird kind of concept. Here's what we do. I'm going to I'm going to try every single coordinate. I'm going to fill in every possible xy coordinate. Between negative 300, negative 300, and 300, 300. I hope you see that, because x is going to range between negative 300 and 300, and then y is going to range between negative 300 and 300. It's always one less than this last one. So that means it's going to try every possible one, and I can fill them all in if I needed to. And that's all I have to do. So because this graph is kind of very zoomed in, I'm going to scale my xy. I'm going to scale it a little bit. So I'll have a 200 to 1 zoom level. So every xy that I get, I'm going to pretend that it's really x over 200, y over 200. Okay, that's all. And then I'll graph it. This zooms in the graph. Okay. All right, so really, I'm going to pretend that I'm working with x chord, y chord. And that will be what I'm trying to see, if this is in the Mandelbrot set. If it's in it, I want to color it in. Okay? It's like part of this cool bit in the middle. I want to color it in if it's in the set. I don't want to color it in if it's out of the set. Okay? So that's how I'm going to code this up. So try every pixel. See if it's in the set. And color it in. If so. Okay? That's all. So I made a function. If it's in the set, well, let's color it in. Let's go to that coordinate, the original one. Put the turtle down, fill it, tell the turtle to go forward 1 pixel. Fill in that 1 pixel, please, and then pick himself back up. Okay, this update refreshes the screen for a reason I'm going to talk about later. Now all we have to do is code up this isPoint in the Mandelbrot set function. So this works on complex numbers. So Python does have complex numbers. You say complex, then the real part, then the imaginary part. You thought you'd never use complex numbers ever again, didn't you? So you turn this into the complex equivalent, and then we can do the actual process of determining whether it's in the set by doing like the cool stuff. We iterate this function. Boop. This one right here. All right, so what we do is start z at 0. That's the first index. That's the first part of the sequence, and we keep on updating it, finding the next element of the sequence. Z equals z squared plus num. I'm gonna do that 100 times. All right, so 100 times, please. Do z equals z squared plus num. And then, if after doing all that, see if z is still small. So we need to see if it's bounded, and that's a way of approximating boundedness. See if it's still small after trying it 100 times. Maybe if you tried it for more, it might have diverged, but we don't care. It's good enough for our purposes. And so then we need to figure out if it was bounded, so we'll check the magnitude of this complex number, and abs on a complex number returns their magnitude. All right, so if it's smaller than some value like 100, I'll say yes, it didn't diverge. It's in the set. Otherwise, return false. And at that point, we have a program. It's going to try every pixel, scale it a bit, fill it in if it's in the set, and just go from there. So I really encourage you to study this code because it's really cool. And so I have my turtle color in blue, the Mandelbrot set, and the turtle goes very, very slowly because there's a lot of little pixels to fill in. I'm going to try this big entire square if you can see my mouse. So he's working away. We can make him go a bit faster by making him not update every frame, like every 500, every 5,000 pixels, please. Then you can update yourself. It makes it go a bit faster. We say turtle.tracer 5,000. New and improved turtle 5,000. And so it doesn't update as fast, but it draws faster. So I believe we have a Mandelbrot set on our hands, and this is really beautiful. This is not a recursive program, but it's a recursive fractal, of course. And we get exactly what Wikipedia has, just a little bit less cool looking. We can make it cooler looking, and I encourage you to come to office hours if you want to know how. And so we have the Mandelbrot set plotted, and we have an extra little turtle to make it even better. Okay, so that's how we can use code to do some beautiful things, I think. And let me give you one more fractal now. This is called I think this is a German name, so it's probably the Koch snowflake. And here's how you generate it. You start with a triangle, and then you divide every line inside of that triangle into thirds. Like that third, like that third, that third, that third, that third, that third, that third. And then on the middle third, you stick it out. A new triangle. Okay? See how they did that? So now we have like the Star of David. And you just do that again. Like divide this into thirds everywhere. And then stick out the middle part. And you can do this forever. And that is a fractal called the Koch snowflake, which is beautiful. Very cool looking. And I think that's where I want to stop. We have a few more slides, and we'll just do that after Thanksgiving. All right, in the last week of classes, I guess. So that's all I have for you. Hopefully you enjoyed the Mandelbrot set. Very beautiful. And I'll be posting all this code as usual because it's not part of an assignment anymore. And yeah, I think that's all I have for you, and I will see you later. Have a good Thanksgiving.